Start with the design aspects and the demonstration. Solar panel is implemented with a variable DC supply with drooping characteristic. The boost circuit then raises the voltage level to required levels. Now this DC capacitor link voltage is sensed by the analog to digital converter ADC of TI Delfino F28335 microcontroller unit. This capacitor link voltage may go up to 350 volts. Microcontroller supply is derived from a desktop computer, and for the remaining electronic circuits, a regulated supply box is used. The input voltage to ADC sensing circuit has been level shifted by TL084 operational amplifier. To limit magnitude of input voltages applied to the microcontroller board to below 3.3 volts, TI's LM7805 regulator, potential divider circuit, and clamping diodes are used. This voltage obtained is sensed by the microcontroller, which is then used to correlate with frequency to generate a sinusoidal wave using voltage by frequency algorithm. Now for diagnostic purpose, TI's TLB5616 12-bit voltage output digital to analog converter DAC is used. Now V by F algorithm shall be demonstrated. V by F control enables high starting torque and avoids the high inrush current associated with direct online type of starting. The upper limit on frequency is decided by the DC bus voltage of inverter, which is sensed continuously. Here, the frequency is generated in such a way that initially it takes some time to reach to the desired frequency. This can be seen in the waveform on the DSO. Normally, a compressor motor of the refrigerator is a capacitor start and capacitor run type single-phase induction motor. It requires 90-degree phase difference between the main and auxiliary winding voltages for starting. In this project, we have eliminated the need for a capacitor by providing a 90-degree phase shift in the waveforms, as can be observed from the output on the DSO. After the algorithm, the microcontroller outputs a PWM pulse train. As we can see here, the PWM output obtained from MCU is of the order of 3.3 volts. Now, to drive the inverter switches, voltage levels need to be increased to 10 volts. Therefore, a scaling circuit is required, which is made by using TI's comparator LM339N. Now, these pulses are given to the switch from this point. Here, a 3-leg inverter in a different configuration is used, as shown in the diagram. 2 legs of the inverter get 0 degree and 180 degree phase shift, and the third gets a 90 degree phase shift. Instead of a 2-leg configuration, this new configuration allows 41.4% more output from the same DC bus voltage. We shall now move on to the motor and see how V by F algorithm controls it. As we can see that initially the motor runs at a low speed of frequency and then slowly builds up to the desired frequency, which should come for the corresponding value of voltage in a stipulated time period. This allows us to match the ramping rate of the inverter's frequency with starting time of the motor. So now, when that value of frequency is reached, the motor continues to run at that particular frequency only. When voltage is varied, we can see that frequency is adjusted accordingly. We have also added a current sensing circuit that gives protection at two levels. At the first level, if current exceeds set current, further acceleration of frequency is stalled. In the second level, if current in the motor exceeds the safe limit, then the inverter pulses are stopped and motor comes to a halt.